Good morning, everyone. I hope you're all staying safe and well. Welcome to the session. During the next 30 minutes, we'll talk about security landscape for smart connected devices in the AI and 5G era. So let's get started. 5G represents a revolution in mobile technology, performance that will rival wireline networks. We're still in early adoption curve, and there's a range of performance targets being cited out in the market. In general, relative to the 4G predecessor, 5G promises up to 10x higher throughput data rate, 100x higher capacity, about 10x greater device density at about 1/10 the latency. With peak data rates going from 1 Gbps to 20 and latency going from 10 to 1 millisecond, 5G will really open tremendous opportunities to host a real-time application and services. While all the previous generations, the predominant use model for mobile phone was primarily internet and talking and texting. With 5G, the vast majority of endpoints will be the things of Internet of Things, and they will be supported by higher connection density. They will look like a sea of smart, fast, connected devices. And we'll go into a little bit more details on what we mean by smart, fast, and connected. Not to worry, I mean, mobile phones will enjoy lightning fast connections and high performance applications leveraging this higher bandwidth delivered by the network. As we enter this era, real time, like I mentioned, is critical because in parallel to the rollout of 5G runs the rise of artificial intelligence, as you can see. AI is increasingly moving into controlling devices in our physical world. Many times you could see them from delivering drones to autonomous vehicles and high-speed, ultra-reliable, low-latency communication that links those 5G networks. And to achieve its latency targets here, 5G will move more computing to a growing number of nodes at the edge of the network for AI inference and even in some cases training. The combination of high bandwidth and low latency delivered by 5G networks and devices will truly enable ubiquitous AI across a broad spectrum of endpoint and use cases. So far, we've talked about 5G and how it enables AI. Vast number of 5G connected IoT devices will generate tons and tons of data. This will build on the wave of data that will be created by billions of mobile phones out there that will be enjoying high bandwidth connections. And it's more like a true virtuous cycle where 5G networks will make possible the collection of this enormous quantity of data. AI training will require these vast amount of data, and AI will be the only practical means to manage this data, to process this data. So as you can see, this marriage of 5G and AI will create enormous value, change the way we live and how we make decisions. 5G will be offering a different level of service of different kind of devices through software-defined networks and network slicing, will be far more complex than its predecessors. So what we have discussed so far is the value that's being created and how the landscape is changing. This distributed architecture will enlarge large number of nodes that will be secured and locate them outside the hardened device center environment as go-to edge. So the bottom line is this. With this greater value comes increased motivation to hack, and more vulnerabilities will be out there when you put the AI and 5G together. And that would clearly mean there is a higher probability of an attack by an adversaries. So now let's look at the AI assets that will be at risk with this high-speed environment. Mainly, we are looking at three product families. Data center, edge node, and the endpoints. The threats are many, whether it's malicious denial of use or intent to steal valuable assets. The attacks can occur at multiple layers, as you can see on the screen. Could be software, firmware, hardware layer, or across the network from the core to the edge or to the endpoints. In today's webinar, we will cover these three with a couple of examples in each one of them and how we can actually secure that particular use case. It'll be critical to safeguard the data carried by these 5G networks, as well as the data that's on these devices. AI-powered devices flying our skies, driving our roads, and protecting our neighborhoods. Any kind of attack which compromises this data can threaten our privacy, property, and personal safety. Now let's, as we have defined the high-level vulnerability and why the higher value real-time nature of AI 5G era will create more vulnerability, let's talk about the basics just for briefly on security. When we think about securing any electronic system, connected devices, or a 5G network, we need to address four fundamental security concerns. Confidentiality, which means preventing access to information by entities you do not wish to share it with. Integrity, making sure something has not been modified and it is as it was intended to be. Authenticity, making sure something is genuine. And finally, availability, making sure something can be used when needed. And this would be the most hard-pressed because things move fast in the AI 5G domain specifically. So with this high-level security framework, let's now dig a little bit deeper into how we secure this data. Fundamentally, we are looking at our need to secure the data when it is at rest. For example, when it's residing within a device or at a server or a mobile phone or on a drone or in a car. And also securing when this data is in motion, when the data is being exchanged between the devices. And there are methodologies such as encryption using cryptography techniques, symmetric, asymmetric, and various other things to fundamentally protect the data at rest and while in motion. Now, one thing to note here, anytime we look at security threat models, we have to assume we are operating in zero trust environment. Adversaries will absolutely get possession of endpoint devices at certain point, and realistically will be able to gain access to the edge devices. Given their great numbers, so vulnerability could exist somewhere. These devices will need to be hardened from side channel attacks, more so compared to secure hardened system somewhere on the data center, because these devices are out in the field, most of these connected devices. Otherwise, the attackers will be able to bypass the strong protection of encryption, and they will be able to extract keys and other private information. So let's dig a little bit deeper as we are defining and kind of peeling the layers on what we need to do. Let's look into the architecture for security. I've just shared a couple of keywords here, zero trust environment. And the second one we want to emphasize is when we look at implementing security as an architecture, we always start with a basic principle, which we call security by design, not by obfuscation. And I want to cite one of the seminal papers Microsoft has written on 7 properties of the connected devices. And those properties are relevant here in the 5G and AI era as well. There are 3 components of this approach. First, the hardware root of trust. And the key here is hardware root of trust, not a pseudo root of trust. It can be built into chips, powering the devices in the core, edge, or the endpoints. Second is really, once you are storing your secrets or keys, somehow giving them unique, immutable identity to those keys and protecting that secure data while provisioning these chips at the time of manufacturing. Third, and important once the device is in operation, is to secure the data traffic that moves across 5G network in this case, and can be secured with the protocol engines and network traffic security. So just like the hardware root of trust, these are built into communication chips, the secure protocol engines, MACsec and IPsec to be more specific, in various devices, whether they are at core, edge, or the endpoints. Through the key management services that are enabled by that unique identity, the chips and devices can be provisioned with keys that can be securely managed via the cloud over the entire device life cycle. So to summarize, these three components, the hardware root of trust, provisioning and key management, and securing the traffic, networking traffic, could provide a fairly robust, secure by design approach towards this problem. Now let's go into a particular device. So take an example of a component of a generic edge device example. One thing to note, this is really a simplified model. We are leaving out a lot of details for clarity here. This device has an SoC, as you can see. It has a CPU, application CPU, some SRAM. Typical device will have some sort of MAC-based multiply, accumulate, ML accelerator IP, typically embedded on a SoC, all of that together. The device outside of the SoC will have some flash memory, obviously a network interface, probably a Wi-Fi. There may be another interface that connects to the cloud servers and other network resources. And if we want the device to be useful, it would have some sensors, maybe audio or video sensors, some sort of user interface. And depending on the type of the device, it could be a speaker, some LED or LCD screen, many other things that can communicate with the outside world. Potentially, it will have some sort of actuators, motors, or other things that can actually give you some sort of activity in the world outside of this device. This edge device, pretty generic. It really applies to a lot of different things. Practical examples could be a smart speaker, could be an AI-enabled security camera, could be a smart automotive sensor of any type, robot, or any other type of device that all actually will eventually look quite similar despite the different use cases. So we have now kind of bound, in order to go forward with our security use cases today, a typical AI device here. Now let's look at the operation of this AI device, edge device. First off, the CPU is going to boot using software that's stored in the flash. And the SRAM will provide the memory for the CPU to execute. Next, you will have CPU that will load an inference model from the flash, and it will load onto the ML accelerator. Now, these weights and activations that are typically involved in an AI application will effectively be stored in SRAM. It's not showing here directly. SRAM could be an accelerator as well. Sensor data will come in the form of sensor from the accelerator. It will perform some sort of inference operation, and the inference results will be acted on by the CPU highlighted here. Now, the action may be showing something on the user interface, activating the actuators or sending results or messages over the network interface, or probably some combination of these. Now, that's a normal operation. One other use case is extremely important. earlier, if you look at non-AI edge device, you just need to update the firmware securely over the air. But in case of an AI device, you can also update models by downloading them over the network interface and storing those in flash. So that's kind of a basic operation of the edge device. Important to keep in mind this additional requirement on security coming from the weights and models and inline encryption in some cases. So we have looked at now how a typical, what are the components of an edge device and how it operates. Now let's try to see how we secure it. And we have talked about the three examples, which was hardware root of trust, network security, and provisioning and key management. Let's see how the hardware root of trust fits onto an edge device here. We can embed this hardware root of trust core in the edge device SoC. This root of trust, hardware root of trust, will have its own SRAM and OTP memory that's not shown here. It will be inside the red box here. It will have access to the CPU, DRAM, flash accelerator, and the network interface over the system bus. It may also have connections into the SoC hardware, including control or monitoring of the reset, test, and debug, and some other system features to really implement it in a secure by design way. With this implementation of insertion of a hardware root of trust inside an edge device, let's peel further another layer on this onion. Earlier you saw that dark blue box that was HRT, the hardware root of trust. Now let's dig deeper into it. What are the characteristics of an ideal root of trust? A hardware root of trust can be embedded, in an AI SoC. Ideally, it should have the following characteristics. Should be purpose-built for security where complexity is minimized, so it can be hardened against the attacks. It silos the cryptographic operations away from the main processing, so the main processor can be optimized for performance. This siloing is a key artifact of this architecture. Otherwise, there is too many ways how a CPU could be made vulnerable. It should offer a full feature set for executing complex algorithms and cryptographic protocols. It should use a layered security model with the hardware, multiple layers on the software, with the flexibility of the software to be able to offer application level support. So whether you would like to use certain standards or certifications to use in the application domain, it should include a strong anti-tamper feature to guard against the side channel attacks such as DPA or even fault injection. From an implementation point of view, you see it could have a basic lightweight state machine, which will be appropriate for a high volume AI-powered IoT device, or a very sophisticated programmable secure coprocessor, in this case, a RISC-V CPU, to secure high-value AI devices. In the next slides, I'll show three examples of how a hardware root of trust can be used to protect the AI hardware, the inference model, and the inference data from attackers. So let's start with protection of an AI accelerator. Unlike data centers, servers which are in a hardened environment, edge devices are far more vulnerable, as you have seen, to the hardware attacks. The solutions for protecting from tampering or denial of use is system monitoring. That's one of the key attributes. A hardware root of trust can monitor the system status, and it can monitor memory contents and detect tampering activity. It can also detect attacks like fault injection if you have the right cryptographic core functionality. It can monitor, test, and debug logic hardware configuration and other hardware status in the SoC using dedicated connections into that logic. It can also monitor ML accelerator operation, making sure it's operating only when expected. It can periodically hash known SRAM state to detect tampering. It can periodically hash invariant flash data and make sure that's not changing. And the internal logic in the hardware root of trust can detect physical attacks like the fault injection, as we discussed. So all in all, it can also monitor network traffic, looking for anomalous traffic that might indicate an attack or a compromised software stack. So this use case talks about protecting the hardware, AI accelerator, the edge device. In the second example, protecting the inference model deployed in an edge AI device. We can use the techniques for signing, authenticating, and encryption to protect our inference model, which is also subject to tampering or replacement or theft. That I have discussed earlier that in an AI era, this is an increased surface area for attacks. In a normal device without AI, you don't have this larger models and weights and activation that you need to protect in some cases. So it's also subject to tampering and replacement or even theft. Adversarial attacks could be possible as well. Once training is complete, the resulting inference model should be signed and encrypted. The signed encrypted inference model is usually stored in flash. Even if the flash is read, attackers still won't have access to the inference model. The hardware root of trust that is reading the inference model from flash, that decrypts it securely and hashes the decrypted data. Next stage is this hardware root of trust verifies the signature and compares it to the hash. Only if the hashes match with the model to be loaded onto the accelerator. Of course, we don't have to keep that decrypted data in memory unless it is needed. So when we are done using it, we can flush it out so it's not accessible to the accelerator. So that's a typical example how you can protect an inference model. Now the third example and the last one.
Neeraj?
Yeah?
I'm sorry to interrupt, but we're running over and I want to make sure we have some time for Q&A.
All right, so I think I'm on the second last. Let me rush through this. Final example use case, let's look at protecting inference results from tampering by an attacker. So if you look at, so the host in this case communicates with the edge device over the network interface and bridges communication over PCIe. And I don't have to go into details, it's very similar to the last one. You can do various integrity checks with hardware root of trust in place, similar to inference model protection, and the encryption of the data provides another layer of protection here when you implement it. Even if the inference results are intercepted by an attacker won't be able to read them. So since we are running out of time, let me go straight to the summary. 5G high bandwidth and low latency, as you have seen, will deliver ubiquitous AI all over the place. It will enable real-time applications. Higher value of data and increased network vulnerability will increase the risks and need for security. We believe multi-layered security protects the data at rest and in motion. And the hardware root of trust security anchored inside an SoC will provide the highest level of protection. This root of trust embedded in an AI edge device will protect your physical hardware, inference model, and inference results. And starting with the basic principle of security by design rather than obfuscation, you will be able to help secure your smart, connected, fast devices in the AI 5G era. So that concludes my session this morning. Really appreciate your time, and we're open for questions.
one question was the attendees saying, architecting for security is a clear need, but do you see a need for the hardware root of trust being built into the AI accelerator as opposed to being a separate SoC, standalone SoC?
Yes, and that is a major trend. I can cite an example of one of the leading OEMs where they have common criteria, level 4 certified, root of trust integrated into an application processor. And we are talking to various other OEMs and industry leaders where we clearly see a trend. And it's primarily, look, if we go to the basics of semiconductors, integration is the name of the game, right? We have all these functions being integrated inside. But in this case, integrating it inside provides larger degree of freedom on how you can use it, especially when you have latency in mind. You should be able to create, because this is an era where you see heterogeneous compute, right? In the old era, you had a couple of ISAs and a couple of GPU leaders. Now you see tons and tons of new architectures coming in with their own. If you look to Google TPU or any of the industry leading AI chips, generic chips are losing market share, even from the large semiconductor companies. So we see clear trend in integrating a sophisticated hardware root of trust inside an AI edge device. I would even go one step further. We are discussing with smaller IoT microcontrollers where earlier they used to be able to just say, we're happy with TRNG and AES. Now they are asking for a lightweight state machine-based root of trust integrated inside the microcontroller. So that is a clear trend we are seeing in the industry. Did I answer your question, Bob?
Yes, thank you. It was an audience question. Hopefully that answered the question. Another audience question. Will the hardware root of trust interfere with normal computing traffic, meaning slowing down just normal operation?
Well, it depends on how you architect it. The way we propose the architecture, you remember the word I used was siloed. When we implement a secure coprocessor subsystem, we want to make sure that if you need to inline encrypt and decrypt, you do that, whether it's over PCIe or any other interface with a whole bunch of very high throughput AES, GCM, or any other crypto cores. So you could actually take care of encryption, decryption at higher performance, high throughput, high speed, separate to the hardware root of trust. And it does not interfere in the general operations because the architecture is siloed architecture as a crypto subsystem, security subsystem.
Okay, thank you. I'm not sure if this is, really a security question, but maybe you've seen this in the context of edge devices. Have you looked at how federated machine learning fits into this picture?
Could you share with me what you mean by federated machine learning?
I think it's the issue of training getting pushed out to the edge, basically.
Yes. So during my presentation, I had said that in some cases, even the training. So one of the customers is using our root of trust for one of the Super 7 cloud data center chip. So we do see when some of the training is being pushed out, it is in many cases for privacy or latency reasons. And yes, there is a clear implementation use case. I didn't go into the detail of that. I just looked at the 3 use cases. So yes, the short answer is yes, in the interest of time.
Okay. All right. Unfortunately, we're out of time, and I know that you're not going to be available during the breakout sessions. What's the best way for our audience to contact you or to contact Rambus for more information?
So you could reach out to us, rambus.com/security, a little plug there. And you will find all the information, including contacting us right there.
Okay. Thank you very much, Neeraj.
Thank you.